Hello, welcome again everyone to another pre-recorded lecture, and for this video we would be talking about the analysis of trusses using method of joints. But before that, let's have a little bit of an overview in the term truss. So as per the definition that was stated by designingbuilding.co.uk, a truss is a structure that consists of members organized into connected triangles. So these structural members right here is what you would be calling trusses. So it is said here that it is organized into connected triangles. So as you can see here, there is a triangle here, and there are also plenty of triangles there. And it is also said here that their overall assembly behaves as a single object. So this collection of members right here would behave as a single object after. So suppose that a certain car would pass through this bridge right here, and let's say that that car weighs about 2,500 kilograms. Of course, if the car would pass through here, its weight would be transferred to the flooring. And the use of this truss right here is to distribute the load of the car to each of these structural members. And those forces are what we call bar forces. So asterisk, bar forces. And this bar forces right here is the magnitude or the forces that each of your structural members would carry. So for example, once again, that you would be having a certain car passing through this bridge right here, its weight would be distributed to these members right here, and the weight that these certain structural members would carry is what you would be calling bar forces. And for bar forces, you would be having two types of bar force. So the first one would be tension, and the other being compression. So for your tension, your member here is to be stretched. And for compression, your member here is to be, of course, compressed. So it would be as simple as that. So by the way, guys, you would be having three parts of a truss. So these members right here on the top is what you would be calling top chords. So it would be self-explanatory why it is called top chords. So top chords. So if that is to be top chords, of course the one in the bottom would be your bottom chords. And all of this in the middle would be called web members. So the one in the middle of your top chords and your bottom chords is what you would be calling web members. So your trusses are most commonly used in the bridges, roofs, towers, and etc. So in the example to your left, so this would be an example for your roof truss. So for example, that you would be installing your roofing materials there, and of course, your roofing materials would have corresponding weights. So its weights would be transferred to the truss, and in the truss itself, all of these members would be having certain bar forces. So may it be in tension, may it be compression, the loads would be distributed to these bar forces to make your structure stable. So this right here is your different types of trusses. So may it be king post, queen, how, fan, etc. But in our pre-recorded lecture right now, we are not concerned with the type of trusses. What we are concerned is their individual bar forces. Okay, so once again, our topic in this pre-recorded lecture would be about method of joints. So for example, that we would be having a certain truss. So for example, this is to be our truss, and once again, this is to be the top chord, this is to be your web members, and this is to be the bottom chord. So in method of joints, so this is actually the easiest method in the determination of our bar forces. So for example, that we would be having a certain force right here. So of course, these members right here would have corresponding bar forces. So meaning they would be carrying this load right here, and they would be having, of course, bar forces. So for us to determine the bar forces, so for example, that there would be a support here. So if this is to be your load, your reaction here or your support reaction would be acting here. So it would be upwards, and this would also be upwards. So for us to determine the bar forces here using method of joints, so we would be analyzing each of these joints, and we would be considering that each of these joints right here is under static condition. So meaning by static, it will not move. Or once again, if you are to talk about statics, meaning that your summation of forces horizontal and summation forces vertical would be equal to 0. And if we are to determine the bar forces here, so for example that you want to determine this, the bar force of this certain bar right here, so we should convert this bar right here into a certain force. So that is your bar force, of course. And for example that this is to be the bar forces here, so you would be analyzing this part right here and use these equilibrium conditions right here to solve for these members right here. So it would be as simple as that. By the way guys, if you are to convert a certain member into forces, it is better for us to assume that it is under tension. And if our answer would be negative, then it implies that our assumption is wrong. So if our assumption is wrong, so it means that that bar force is to be in compression. By tension, so for example that we would be analyzing this joint right here. So once again, your tension is to be in a pulling action, in a pulling manner. So meaning our force would be away from the joint since it would be pulling. So this would be tension. So this would be tension, this would be tension, and this would be tension. If once again you would be considering this joint right here, it is better for us once again to consider this in tension, this one in tension, and this also in tension. So once again, you would be assuming that your bars would be pulling your joints, so tension. Okay, so I think you're already confused, and if you are, it is better for us to have an illustrative example instead. Okay, so for our illustrative example, we would be solving for the bar forces of this truss right here. So the first thing that we should do is to draw its free body diagram. So I would now be drawing its free body diagram. Okay, so now that I have drawn my free body diagram, so I have realized that I have no space in here, so I would be copying this to the next slide. Okay, so now that I have my free body diagram already, I would now solve for the reactions. And I would now solve for this reaction via the equilibrium condition of this truss. So if I would be getting the summation of forces horizontal, so summation of forces horizontal is equal to 0, and I would be assuming to the right positive. And by that, our only force in the horizontal plane is only AH. So AH is equal to 0. And as for your summation of forces vertical, so if that is to be 0 and I would be assuming upwards is to be positive, so AV, so that is the vertical reaction of A, and minus 75 kilonewtons minus 50 kilonewtons. So this would be these two forces right here, and it is negative since it is downwards. Okay, as for your AD, that would be positive since it is pointing upwards, so plus AD. So it is equal to 0. And simplifying this term, so AV plus AD is equal to, so I would be transposing the ones in blue to the right, so that is to be positive 125 kilonewtons. So let's confirm. So 50 plus 75, that is to be 125. Okay, and since we have two unknowns, I would just be labeling this as equation number 1. The summation of moment about a point is equal to 0. And I will be assuming that that point would be A. So summation of moment about A is equal to 0. And let's assume that clockwise is to be positive. So if we are to get the moments of these forces right here about point A, so for 75 kilonewtons, 75 kilonewtons times the lever arm. The lever arm is to be 4 meters. So 4 meters. So plus 50 kilonewtons. And by the way guys, both of these are positive since it would give a clockwise moment if you would be fixing this point right here. So if this is to be your point, this is to be your lever arm, it would turn in this manner. So there, 50 kilonewtons times what would be the lever arm of 50 kilonewtons, that is to be 4 meters plus 4 meters. So 8 meters. Okay, and as for AB, so that would be negative since it is, it would give you a counterclockwise moment. So minus AB is equal to, minus AB times the lever arm, and the lever arm is to be 4 plus 4 plus 4, that is to be 12 meters. And that is to be equal to 0. And in this equation right here, we only have one unknown, so we can actually solve for AB. So I would be transposing it to the other side. So 75 times 4 plus 50 times 8. So that is to be equal to positive 12 AB. Now solving for AB, divide both sides by 12 to isolate the variable AB. So AB is now equal to, so looking at the calculator on your left, so that is to be 75 times 4 plus 50 times 8 divided by 12. So our answer for our AB would be 58.3. So this is to be for AB. And as for AV, so I would just be copying this to the next slide since I don't have any space. So AB. And our equation number 1 is, oops, by the way, that is to be AD, I should say. So AD, so that is to be AD. I'm sorry about that. Okay, so if that is to be AD, okay, using this value right here and this equation right here, substitute AD. So once again, AD, substitute AD in equation number 1. Okay, so by that, AV plus AD, and our AD is 58.3 kilonewtons is equal to 125 kilonewtons. So now solving for AV, AV is equal to 125 kilonewtons minus 58.3. Now we would be having an answer for AV as, so 125 minus 58.3, that is to be 66.7. So we now have our reactions. So that would be this. So I would now be deleting this since we don't need this anymore. But I would just be putting it here. So for AD, that is to be 58.3. And for AV, that is to be 66.7. Our next step now is to convert our bar members into their corresponding bar forces. And once again guys, it is better for us to assume our bar forces to be in tension. And if our answer would be negative, so it would mean that the bar force for that particular point, for that particular member, would be in compression. So okay, I would just be doing it this way. So and I would be converting them to tension. So this is to be in tension. Emphasis everyone that I have assumed my bar members to be under tension. And if it is under tension, the tendency of your bar members is to pull your joint. So for example, that you would be analyzing this certain joint right here. And as for this bar force right here, it is pulling this joint. And as well as this joint right here. So this joint right here is being pulled by all of the members, and as well as this joint right here. Okay, so what would be our next move? So our next move is to compute for the bar forces. Okay, so it would be up to you on where you would start in the method of joint. So you can start from here and you can also start from here. And in my case, I would want to start in this joint right here going to the right. But once again, it would be up to you. So if I would be choosing this, I would now be drawing this free body diagram here again. So it would be like this. So okay, so this is to be FBD A. So FBD at joint A. So this would be its forces. And this member right here is AB. So if that is to be AB, this is to be FAB. And if the one on the bottom is member AE, so this would be FAE. Okay, so now I would be solving for this using the equilibrium conditions, summation of forces horizontal and summation of forces vertical. Okay, so for the summation of forces horizontal, summation of forces horizontal is equal to 0, and I would be assuming to the right is to be positive, so that is to be AH, but since AH is equal to 0, I would not be including that. And as for FAB, so FABX, so the X component of FAB plus FAE is equal to 0. But if we are to get this value right here, and once again, if you would be looking at this slide right here, the slope of this line right here is 3:4. So drawing that, this is to be 3:4. So 3:4. If that is to be 3:4, the hypotenuse of this slope right here is to be, so 3 squared plus 4 squared. So square root of answer, and that is to be 5. So Pythagorean theorem, this is to be 5. So if the slope is to be 3:4, you can use this values right here to solve for this angle right here, or you can just directly use this. So if I am to directly use this, so that would be, so FABX is equal to FAB times 4/5, or 4 is to be the adjacent side and 5 is to be your hypotenuse. Or if, for example, that you have your angle right here, that is to be FAB cosine theta. So you can use this or you can use this. So whatever the case may be, or whatever method you would choose, your answer should be the same. So okay, but once again, since I am given the slope, I would use this formula instead. Okay, so plus FAE, that is equal to 0. So let's say that that is to be equation number 1. And for the summation of forces vertical equal to 0, then let's assume that upwards positive. So that would be AV, so 66.7 kilonewtons plus FABY. So that would be the Y component of FAB. So is equal to 0. For us to get for the value of FABY, so I would be rewriting this. So 66.7 kilonewtons plus FABY. So plus, what would be our FABY? That is to be 3/5 FAB. Or if you are given the angle, that is to be FAB sine theta. So both of these values right here should be the same. Since sine theta, so if you can remember SOHCAHTOA, so SOHCAHTOA, so sine is sine theta is equal to opposite, and our opposite here would be 3 divided by a hypotenuse, and our hypotenuse here would be 5. So basically, sine theta and 3 over 5 is equal. So it would be as simple as that. Okay, so solving for the value of our FAB. So 3/5 FAB is equal to negative 66.7 kilonewtons. Okay, and cross multiplying, so our FAB is now equal to, so negative 66.7 times 5 divided by 3, and our answer here would be negative 111.16. So negative 111.16 kilonewtons. And this negative symbol right here implies that our bar force is in compression. So there, I would be copying this here since we don't have space. And I would be deleting this already. So okay, since we already have our value for FAB, so substitute FAB in equation number 1. And since our FAB is negative 111.16, so negative 111.16 kilonewtons times, well, 4 over 5 plus FAE is equal to 0. So using this equation right here, your FAE is now equal to, so I would be transposing this term right here. So 111.16 times 4 over 5. So our FAE is now equal to times 4 over 5. So our answer here would be 88.928. So 88.928 kilonewtons. And since it is positive, this is to be in tension since my assumption is correct. Okay, so that would be the value for our FAE and FAB. So I have already listed our answers here. So for FAB, which is this force right here, that is to be 111.16 compression. And as for FAE, or this one right here, that is to be 88.928 kilonewtons.